Hello and welcome to Module 3 of Chapter 17. In this chapter, we will be covering the subject of superposition, which is basically a continuation of what we have done in the previous chapter, traveling waves. Before I begin, let me just talk a little bit about the course schedule and what we are doing. I hope all of you are checking this area in the course schedule. I have posted that since day one, and it basically just gives you the schedule of the course for the rest of the semester. And I always update that schedule. So just to let you know, we are right now in Module 3, and we are covering Chapter 17, Superposition, which I'm going to talk about today. And then we will have the midterm exam starting. We will have it this coming week, and that's going to be on the 24th. So I haven't prepared the midterm exam, but it will open up on Friday the 24th, and it will close on the 26th, and that will be from Friday to Sunday. Let me show you the calendar. So it's going to open up on the 24th. Next week, and then it will close on Sunday. Okay, the midterm is gonna cover the chapters that we have not covered in the midterm one, and they are chapter 20, 21, 16, and the present chapter. Okay, all right. Let me go to the book, go back to class. So in this chapter, we will be covering the subject of superposition. So what is superposition? When we say the word superposition, when you hear the word superposition, what comes to your mind is an algebraic sum. Okay, what that means is the following: when two waves or more of the same type, say sinusoidal wave, they cross each other at some point. Okay, the resultant displacement at that point is equal to the sum of the displacement due to each individual wave. Let me explain. Let's say, for example, first of all, let's ask the question: what happens when two waves pass simultaneously through the same region? So let's say, for example, I have a wave, let's say y1 of xt and y2 of xt. Okay, so let me represent them. Imagine you have a string, say a guitar string. Okay, and then you have one pulse, let's say is going this way. This is y2, let's call it, and then I have another pulse here, y1, and it's going this way. So those two waves are moving in the opposite direction, and they're about to meet each other on the same string. Let's see if I can draw the same string. There it is. Okay, they're coming toward each other. So what will happen is that they will pass through each other, and they as if the other does not exist. In other words, y1 is going to be here after a little bit. Here is y1 moving on its way, and then y2, it's right there. Okay, however, at some point, at the moment that they will interfere with each other, which is the superposition, what will happen, they will overlap, and you will have a resultant wave with an amplitude that is larger than both. Okay, this amplitude here is larger than y1 and y2 for this case of the wave. Okay, so they have a new amplitude. Let's call it y prime. You get that? So this is where they overlap. So you have here is y1, and here is y2, and they overlap here. So this is the overlap. Okay, let me show it to you from analytically or mathematically speaking. So if you remember from the previous chapter, we represented a wave by y, let's say y of xt is equal to y naught sine kx minus omega t. Remember, the minus sign here indicates that the wave is moving to the right. Okay, and then I'm changing the notation. I believe we used d for y naught, so I'm going to use y. Yes, I'm going to use y naught for the amplitude. Okay, so this is the amplitude. I find this notation a little bit more convenient. Okay, so let's say I have. Let's go back to this picture here. So I have two waves, and they are moving in the opposite direction with the to each other, and I want to find a mathematical way to describe them. So if I represent y1 of xt to be equal to y naught sine kx minus omega t plus phi naught, which is, this is the phase constant. And let's say y2 of xt equals y naught sine kx minus omega t. Okay, what that means that the both of them are moving in the same direction, say to the right, because there's a minus sign here, right? This is the minus sign and the minus sign here, so they're both moving to the right. But there is a way, a phase constant. What does that mean? Let me show you a picture of it. Let's say I have my coordinates here. And let's say I want to draw y2 first. Okay, here's y2. Okay, this is y2. Well, if y1 is different from y2 by a phase constant, so maybe it is like this. Let's say this is y1. If I can draw it. Okay, see the difference between them here? This is the phase constant, phi naught. Okay, I mean, for that case it probably would be minus, but anyway, that's basically, so you get those two waves. This is one here, and let's say they're moving. Of course, they both have minus minus here, which means both of them are moving to the right. Okay, so when they meet each other, so again they have a different in phase constant. When they meet each other, how do they overlap? How does the superposition look like? Okay, in other words, the sum of the two waves, how does it look like? This is what we are concerned about. Okay, so what we want to do simply, according to the superposition principle, is basically it's the algebraic sum of the two waves. Just simply add them up together. Okay, literally y1 plus y2, and you will get the superposition, how they will look like when they overlap. Okay, so let's add them up. So the new wave, we're going to call it y of xt is equal to y1 plus y2, those two waves. Okay, so when I do that, it's going to look something like that. So I have y of xt equals to y naught sine kx minus omega t plus phi naught plus sine kx minus omega t. Okay, now I need to do some algebra to get them to combine together. If you remember from the trick for identity, it says sine alpha plus sine beta is equal to 2 sine alpha plus beta over 2, that's the new argument, times cosine alpha minus beta over 2. Okay, so we're going to use this one for ours, and if you work it out, I'm going to have you do it by yourself. You'll end up with the following expression. I have here bracket 2 y naught cosine phi naught over 2 times sine kx minus omega t plus half phi naught. There we go. So this is the superposition of the two waves. Okay, it's a very interesting relationship, so we're going to study it now. We want to analyze this one. So in other words, when two waves move, okay, they both have, okay, we're talking about what? We're talking about here, we're talking about two waves that have the same amplitude. Why not, right? Let me change the color. This one, I'll make it pink. So we have the same amplitude, okay? They only differ by a phase constant, so one wave ahead of the other, if you will, and they both moving to the right, okay? Have the same omega t. So when they superimpose, interfere with each other, what will happen? Well, the resultant wave would be this one here, okay? So let's make the following. Let's study this equation further. Before we do that, look at the amplitude. What is the amplitude here? Is it 2y naught? No, the amplitude basically is the whole thing. This is the amplitude right here. Notice that the cosine here is a constant. See that? Phi naught over 2. You know, I already know what phi naught is, and so I can just plug it in, and this will give you a number. And this whole thing here is the amplitude of the wave. Okay. I'll give you an example. What if phi naught? Let's assume it was let's say 0. Okay. What does that mean? Go back to the picture. If it was 0, that means I have two identical waves that there is no phase constant and they meet each other. What will happen? In other words, it looks something like that. What will happen if I have two waves, one moving this way, here it is, and then here is another one, is exactly the same, exactly in phase. They both, we call them in phase, because the phase constant here is 0. They both, in other words, peak meets peak, look at that, and trough meets trough, and then I have here peak meets peak here. What would be the resultant wave? Well, you probably from your previous physics classes or something, you probably studied that when two waves in phase, which means the phase constant is 0 between them, what will happen if the amplitude of this wave is A and this one is A, the resultant wave is going to be one big wave like that with amplitude of 2A. Oops, the amplitude would be here, 2A here. Okay, so it will basically double. And also, you probably know if it is completely out of phase, which means if I have a wave like this and then another wave like that, where peak meets trough. See here, peak meets peak, trough meets trough, peak, peak, and then here peak meets trough, and then trough meets peak, and then peak meets trough. You see that? They're completely out of phase, and the resultant wave, they will actually, a total annihilation, they will annihilate each other, and you're not going to get anything out of it, okay? Well, let's see if this equation proves that. So let's assume if the phase constant is 0, which means they both are in phase, okay? So we can just plug it in. So in this case, y, the resultant wave here, the superposition, that is equal to 2y naught. I'm just plug it in from here. Cosine 0, that is. Cosine 0 times sine kx minus omega t, and that's it. Okay, so cosine 0 is 1, so basically we get excuse me, 2y naught sine kx minus omega t, and as you can see, they are in phase, and you will get double the amplitude. You got that? Okay, good. What if the phase here is 180 degrees, which is basically the out of phase? Okay, so they differ by 180. In other words, here is let's say you have a sine wave. For those of you who are not seeing it, let's say I have a sine wave. Okay, this is a sine wave right here, and so of course the one cycle goes all the way up to 2 pi. So this is pi right here. So an out of phase wave would be something like that. I mean, another wave that is out of phase with it is going to be something. I'll put it a different color. It'll be something like that. Oh, you see what I'm saying? And so on, instead of saying. Okay, that's out of phase. Well, let's see that we indeed will get annihilation, total annihilation, or total destruction, or they call it sometimes constructive interference. We're going to talk about that in the next chapter when we cover interference. Anyway, so when we plug in 180 into our equation, this equation right here, okay, we will get, let's see, so in this case I will have y of xt is equal to 2y naught cosine what? Phi naught over 2, which is 180 over 2 times sine blah blah blah, but because this is cosine 90 is equal to 0. You see what I'm saying? I need to get rid of this phone. Hold on, let me just get... back. Okay. You got it? So basically we will get a total, what is called destructive interference, and you will have 0. No wave here. Okay. Let me give you an example of this, a numerical example. So here we have two waves move the same direction along a string, let's say a guitar string or something like that. Okay, and then they interfere with one another. The amplitude of each, is y naught equal to 9.7 millimeter. Okay, and the phase difference phi naught, that is, right, is equal to 110 degrees. Now he's asking what is the amplitude of the superposition. We're going to call it y prime naught. Okay? So all we need to do is go back to the formula that I have just showed you right here. Shall we call it equation star or something? We go back to this equation right here, and this is the amplitude, right? This is the amplitude right here. He wants the amplitude of the superposition. So we're going to take that and write it down. So we have that the amplitude, I'm going to call it y prime naught, is equal to 2y naught. Remember, they have the same amplitude, 2y naught cosine phi naught over 2, right? And we can just plug it in. So we have 2 times 9.7 millimeter. We'll keep it in millimeters, okay? Then we have cosine phi naught is 110 over 2. Plug it in, and then when I do that, let me use my calculator. So we have here, I hope you're working with me. So we have here what is it? Cosine 110 times 9.7 times 2 equals 11.1. So I'm going to get here 11.1 millimeter. There we go. So the resultant amplitude is larger than the 2, if you notice, right? So I mean, ideally, if both of them if there was zero, let's say if there was zero phase difference, then the resultant amplitude would be probably, I mean, it will be double 9.7. So it's going to be 9.7 times 2, right? We're going to be that part, because that will be 1 in this case. Cosine 0 is going to be 1 here. See what I'm saying? Okay. Okay. Now here's another question for this example. He said, what phase difference phi naught between the two combining, did I spell it right? The combining waves would result in an amplitude that is the same. In other words, what would be the phase difference? Find the phase difference such that y prime naught, this one, this y prime, is actually equal to y naught. Okay? What would be that phase? In other words, when they combine together, you still get exactly the same amplitude of the two, of the old two. You see what I'm saying? Well, that's easy. All you need to just, you take the same formula, this one here, and then you equate it to y naught. So it's going to be 2 y naught cosine phi naught over 2. That's equal to y naught. And basically, just solve for phi naught. What is phi naught in this case? So in this case, I'm going to have 2 cosine, phi naught over 2 equals 1. So this gives me cosine phi naught over 2 equals half. And then I work it out. Did I do it right? Should be. And then, so what would it be? Well, cosine 60 is 1/2, and cosine negative 60 is 1/2. So basically, phi naught is equal to plus or minus 120 degrees. So it is, if the phase difference between them 120 degrees to the left or to the right, you will have the two waves will combine, and they will have the same amplitude as before. Okay, the original one. You know what I mean? Okay. Okay, good. The next topic is standing waves, and then I'll have a couple of problems from the homework. Some of the homework problems, I admit, they're a little bit hard for some of you. I'll discuss at least a couple of them. All right, standing waves. If you've never seen, you know what, maybe I should go online and show you a standing wave, because you do have a lab. Unfortunately, we're not doing lab this semester, but if you're taking lab, you can actually do a standing wave experiment. But let me go to the YouTube, and I think you will find something there. Standing waves. Just want to show, oh, this one. This one is a cool experiment. I remember watching it. So there we go.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, it sends a wave. It sends a wave down to this end. The wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go fire. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is,
Keep pushing, you guys.
So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, and the middle's a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5.
So he's getting those waves based on changing the frequency. In the experiment that you would be doing at UNLV would be you have the same frequency 120, but you're getting different standing waves. Sorry, you're getting different nodes by changing the mass, because you have the vibrator here in the setup at UNLV, and then you have this side of the string is hooked up to a pulley, and then the pulley you have a mass at the end, and then you are adding or subtracting the masses, basically varying the tension in the wire, and that variation of tension give you a different standing wave. You see what I'm saying? Here on the other hand, his setup is he has this oscillator right here, and this oscillator, he's varying the frequency of the oscillator. You see what I'm saying? That's the main difference between our experiment and his demo. But his demo is fine. I'll continue watching it.
Now, I can find any of the other, all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3
This one is fundamental.
third harmonic, well, 3 times 8.5, that's 25. And there we go.
Isn't that cool?
So that's the third harmonic. How many wavelengths is this? Well,
1.5
1
and a half, right?
1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high speed camera and verify for yourself that it is 1 and 1/2 wavelengths.
I think I'm going to stop here for that. You're welcome to, of course, to watch it. It's called Standing Wave Part 1 demo. I haven't watched Part 2. Oh, he's going through the mathematics of it. Looks like he's giving. Anyway, I haven't watched that. Anyway, back to class. Okay. So basically, a standing wave is that you have two waves. One wave is moving in one direction, and the other is moving in the opposite direction. Both waves are identical. Then they overlap, and they would form what is called a standing wave. Excuse me, a standing wave pattern. Okay. So let me show you some mathematics of this. So here I have two waves. I have let's say wave 1 is y1 of xt, and let's assume this one is moving to the right. So that's going to be, in this case, y naught sine kx minus omega t. Okay, so this wave is moving to the right because there is a minus sign here, right? And then let's say y2, again, it's an identical wave to it, except it's moving to the left. So that's going to be y naught sine kx plus omega t. You see what I'm saying? Basically, those two waves are really identical. Basically, what you have, imagine you have a string, let's say a guitar string, and here is the vibrator or the oscillator that is moving up and down, right? Some frequency. So it's move up and down. So you have one wave going. Here is the first wave going, okay? And then, of course, many waves are coming. Going, say, to the right. But the first wave that comes in, and then it reflects back. Let me put it in a different color, that reflected wave. It's going to reflect back, and it's going to go like that. You see what I'm saying? So that's the reflected wave. So here you have a reflected wave and an incoming wave. Well, those two waves are identical. It's the same wave, except it's being reflected. Okay? And that's basically the story of those two. So you have one wave incoming, so we can call that incoming wave. And then this is outgoing, or reflected, if you will. Okay? So they're both identical in that sense. The only difference between them is that one is moving to the left, one is moving to the right. That's all. You got it? Okay. And then you would have what is called the standing wave pattern. Okay, the one that you saw in the video. All right. So what I want to do now, I want to combine them together, combine those two waves together, and see what is the resultant wave. So in this case, I'll have y of xt, and that's going to be, when I do it, well, let me just start on it, and then you can work out the details of it. So y1 of xt plus y2 of xt, and these combined together is going to be y naught sine kx minus omega t plus y naught sine kx plus omega t. Then I'm going to use the same identity that I used, you know, the one, what is it? Sine alpha plus sine beta is equal to 2 sine alpha plus beta over 2 times cosine alpha plus beta, I'm messing up, cosine alpha minus beta over 2. You see what I'm saying? You use that, plug it in here, go through the derivation. It's not much really. You'll end up with the following: 2y naught sine kx, okay, times cosine omega t. You'll get this strange looking thing, okay? And this is not a moving wave. You see what I'm saying? This is not a moving wave. It is actually a standing wave, and this term in the bracket is the amplitude. Amplitude. Okay? And let me show you how that works. Look at this amplitude. You will find that certain values of x where the amplitude becomes 0. Why do I'm talking about 0? If you go back, I wish I kept the video, but if you remember how the standard wave looked like in the video, it looks something like that. Remember when he did the lambda plus half, you know, that looks something like that. Let me try and do it. Maybe here. Okay. You got something like that, and then actually it looks more like this when it was oscillating like that, right? And these are called nodes here. Okay, and the wave was also, and these are called the maximum here. This is called antinode here, antinodes, and these are nodes. Okay, so these are nodes here. Okay, and he was able, you can actually put your finger right there, and the wave is still going because it's not a moving wave. You got that? Okay, so these values here, the value is, the amplitude here is 0. You agree with me on that? Amplitude equals 0 here. Okay, so I am interested in what are those values, mathematically speaking. What are they? Okay, so how do I do that? So we can, let me just write this sentence: certain values of x in which the amplitude equals 0. Okay, what are they? Well, it's equal to 0. Remember, this is a sine. I'll use a different color. When this is equal to 0, right? So this amplitude becomes equal to 0. So what values of kx will make the sine equal 0? Well, when kx equal to 0, right, because sine 0 is 0. When kx equal to pi, sine pi is 0. 2 pi, 3 pi, and so on. Basically, n pi, where n here such that n equal to 0, 1, 2, 3, and so on, right? So in other words, those values will cause the amplitude to be equal to 0. But one more thing. But we know that since k is equal to 2 pi over lambda, remember it's a wave number, so I can say that 2 pi over lambda, this value of k, let me say this kx, which is 2 pi x over lambda, when it's equal to n pi, you will get a zero amplitude. You see what I'm saying? In other words, the pi's cancel out here. I will end up with x. What are the values of x where the amplitude is zero? Is basically n lambda over 2. You'll get the nodes basically in the picture here. These x equals 0. You see what I'm saying? Here. Got it? So what are they? Well, look at it. It's half a wavelength. Look at that. Remember, the wavelength is what? From here all the way to here. That's 1 lambda. Well, look at that. At half a lambda, this is lambda over 2, right? And so at half a lambda, you will get a node. You will get the zero amplitude. So at half wavelength apart, the nodes that nodes are, and let me just write it down. Nodes are half wavelength apart. You got that? Okay. Now, the next question is certain values of which the amplitude is a max, which is basically what we call antinodes. That's another word for it. I never use this term, but they're called antinodes. Okay? Well, when? Well, at the maximum, go back to the expression that we have right here. It's a maximum when the amplitude is equal to 2 pi. Makes sense? Excuse me, 2y naught, sorry. So it is maximum. Let me use green maybe. When the amplitude is 2y naught, in other words, when sine kx equal to 1, you get maximum amplitude. Make sense? Okay. So what I want to do now, I want to find what values of kx will make the sine equal to 1. You got it? Okay. So we have sine kx equals 1, which means what values of kx will be equal to 1? Will make the sine equals 1. Well, that will be pi over 2, 3 pi over 2, right? 5 pi over 2, and so on. Basically, remember, these are all odd numbers: 1 pi over 2, 3 pi over 2, 5 pi over 2, and so on. So kx, if I put it symbolically, it's basically n plus 1/2 pi, right? Where such that n equal to 0, 1, 2, 3, and so on. Okay, that should work with that, right? So back to the value here, kx. So we have here 2 pi x over lambda is equal to n plus 1/2 lambda over 2, and where n, of course, the this is n, did I do it right? This is n pi, that will be n pi over 2x. I'm making a mistake somewhere, am I? Maybe I'm a little bit ahead of myself. Hold on. Let me cancel this. Sorry about that. So I have this one now. I need to combine it with, I know that k is equal to 2 pi over lambda. I'm not working, I'm working very fast, sorry. Okay, so I want to take this and put it right here. So that's going to be 2 pi over lambda, this is for k, times x equals to n plus 1/2 pi. The pi's cancel out, is that okay? And then from there, I'm interested in the value of x. So that's going to be n plus 1/2 lambda over 2. And there we go, okay? Where n here is equal to that. And there we go. These are again, they are also half a lambda apart, and it makes sense. Look at the picture here. They are half from here to here. That's a distance or length of lambda over 2, right? So in this case we would have, so they have antinodes half wavelength apart. Okay. Okay, good. Another thing I want to say, the last thing I want to talk about, and that is the fundamental frequency before we start doing some problems. He talked about it in the video as well. Okay. Imagine I have a guitar string, okay? I mean, basically, this is a continuation of standing wave. Let's say I have a string that is tight between two ends here of length L, okay? And let's say I pluck the string and I get this one. I'll make it a little bit smaller. For me, it's easier to draw. I would get this. So if I get this one, so let's say now I'm getting, the string is vibrating in this fashion, okay, up and down like that, okay? So what is that equal to? How the length of the string is related to the wavelength? Well, as you can see here, the wavelength is only half a wavelength. So in this case, L is equal to lambda over 2. Make sense? Now, at a different frequency or different tension, you may get it to be like that. See that? Where here the length is what is equal to lambda. Make sense? Okay. The third one, I'm going to do a bunch of them. You may have a lambda and a half, where it is, here is the length of the string, and then let's say you get something this pattern. That's what we have, what you've seen in the video that that guy had. So in this case, L equals 3 lambda over 2. And then one more. Imagine you would have something like, you get 4 of them here. Like that. In this case, L equal to 4 lambda over 2, and so on. You see what I'm saying? That's basically 2 lambda, and so on. So basically, there is some relationship between the length L and the wavelength that you are seeing on the standing wave of the wavelength, and it's basically n lambda over 2. Okay? If I put everything here over 2, so it becomes here for this case 1 lambda over 2, 2 lambda over 2, and so basically this is the relationship. Where n here is equal to 1, 2, 3, and so on. Okay. Now we know that the frequency f is equal to v over lambda. Remember from last chapter. So that will be equal, if I plug in the lambda value. See this? I'm a little bit ahead of myself. This will give me what? Lambda is equal to 2L over n. Is that right? Let me box that. And then I'm going to plug it back in here. Let me just go here. So we know that the frequency is equal to v over lambda. So in this case, that will be equal to v, or rather nv over 2L, right? So I have here this nv over 2L. Let me box it. And we have that, okay? Now, we define the fundamental frequency f1, I mean, I can, let me go back to this formula. We can also put f sub n, where for any value of n, for example, n equals 1, 2, 3, 4, whatever, so f sub 1, f sub 2, and so on. We define the fundamental frequency is when n equals 1, okay? Which is basically this picture. This is the fundamental frequency right here, okay? N equals 1, okay? So if the fundamental frequency in this case, it will be equal to f sub 1 is going to be v over 2L. This is defined as the fundamental frequency. You got it? Okay. And I mean, if you use in terms of lambda, the wavelength here, for the fundamental frequency, and that will be equal to lambda equals 2L. And the picture, of course, is this one right there. Got it? Okay. I'll show you why this is important when we do. Let me do this problem. I have this exercise not from the book. I have it from my notes. Let me show it to you. And then we'll do maybe a couple of problems from the homework. It says here, let me draw the picture. You have an oscillator or a vibrator. Here it is. And you have a string. It's similar to the experiment that you would have done at UNLV, at your lab class. And then you have a mass here. Okay, and let's call these point P and Q. Okay. The length of the string is L. Okay, and then I'm seeing a pattern that looks something like that. The number here is arbitrary, okay? Trying to make them as similar as possible. But anyway, there we go. We see, and let's say this is the vibrator right there, the oscillator, and let's assume the frequency is given to us to be equal to 120 hertz. Okay, there we go. Okay, so the statement of the problem says you have a string tied to a sinusoidal vibrator, at point P, and the length L, or PQ that is equal to 1.2 meters. Okay, the linear density of the string is 1.6 gram per meter, and the frequency of the vibrator, I already told you that, is 120 hertz. And we have he said nodes exist at Q and P. Okay, fine. Number part A, excuse me. It says find the mass. What mass M right here, right? What mass I can put here? What mass M that allows the setup at fourth harmonic, okay. I forgot to mention what that means, the word harmonic. Okay, going back to what we did about the fundamental frequency, remember, right here. So we say N1, it means we call it also first harmonic. For N equals 2 is second harmonic, third harmonic, and so on. Okay, that's basically the harmonic here is the N number. So first harmonic is first harmonic is N equals 1. Second harmonic, N equals 2, and so on. Got? All right. Okay. So he said, what mass? See, I mean, what will happen if you start adding masses here? Okay, you'll have different patterns here, different harmonics, if you will. Okay, so not each mass, a specific mass correspond to certain harmonics, certain number of fundamental frequencies. Okay, so what mass will give me fourth harmonic? Okay, basically that's what he's saying. So we know that here is the frequency is equal to nv over 2l for fourth harmonic, which means n equals to 4. Okay, remember I am trying to find the mass m. Okay, so in this case I'll have f is equal to 4v over 2l, and that's 2v over l. That's the frequency. Okay, and we know that the velocity, maybe I should put it here, since he gave me the linear density, so that I need to find a way to link the mass with the tension. Well, how is that happening? Well, here is the mass, it's mg, right? So you got mg, and here's the tension, T, right? So T equals to mg. And I know that T is equal to square root of, let me do it. When we know that the velocity is equal to the square root of tension over the linear density, right? So do you see the link there? So he already given me the tension, the linear density right here. And I already know, I have just found out what the tension is. So when I plug it in here, I can solve for m. And what is v? Well, v is right here. Okay, so if I combine all of them together, I can find the mass. Do you see the plan? Okay, so the velocity is equal to LF over 2. Is that okay? That's the velocity. I am solving it from here. The velocity is equal to LF over 2 equals to square root of mg over mu. Square both sides. So I have L squared F squared equals to 4 mg over mu. Okay? Now I solve for the mass. The mass is equal to mu L squared F squared over 4g. Got it? That's it. All I need to do now is to solve for m. So just plug in the numbers. I have them all. The mu value is this. Of course, I need to put it in kilogram. So that's going to be 1.6 times 10 to the negative 3. The length, he said, is 1.2 squared. Frequency, oh, we forgot to get the frequency. Oh, it is 120, right? The frequency is 120. That's the frequency of the oscillator, vibrator, divided by 4 times 9.8, and then you plug in all that in your calculator, you get an answer of 0.846 kilogram. In other words, if I would add here this amount of mass here, I will get a fourth harmonic. Basically, it's going to look something like that. Let me show you a picture of it. So here's point P and point Q. So here is point P and Q. So 1, 2, 3, 4. It's going to look something like that, roughly. There we go. So this is n equals 4. You got it? Okay, good. Try to do number 42. I don't think it's a homework. It's a tough problem. You may want to work on it if you want to. Number 42. I'm not going to do it here, but I'm going to do number 48, and there is another one I wanted to do, number 49. Okay, so let me start with number 48. They're both homework, I think. I'm sure 48 is homework. Oh, maybe I should show it to you on the on the book here. We go back. Keep me signed in. Is it working? Okay. I'll show to you the picture. We are in chapter 17. And it's number 48. So I have to scroll way down. 48. There we go. There we go. Here's the picture right here. I'll make it a little bit bigger. Right there. Okay. So what you're looking at, let me read the problem. Oh, it's only one sentence problem. He said, what is the fundamental frequency of the steel wire? Okay. So what you have a beam. Okay. This is kind of a review of Physics 180. So you have a beam here, the beam of length 2 meters, of mass 8 kilograms, and then you have a steel wire is attached to it like that. It holds the beam in place, if you will. The mass of the bar or the beam is 4 kilograms, and then the steel wire has a mass of 75 grams, which is pretty small. And as a result of that, as a result of this mass, the wire here is, think of it like vibrating, okay? It's oscillating. He said, what's the fundamental frequency, which means what? F sub 1. What's the fundamental frequency of the wire, okay? So I can find the fundamental frequency if I know the tension. You see the plan? When I read a problem like that, first thing that comes to my mind, I need to know the tension inside the wire. So that's required mechanics. That's required Physics 180. I need to set up the free body diagram, get the forces, possibly get the torque, and then work it out and then get the tension. Once I get the tension, I'm done. Basically, now I know the velocity, and the velocity, then I know from there, I know the fundamental frequency, because there's a relationship between velocity and fundamental frequency, that is. Okay, so that's the plan. So first I need to draw the free body diagram. So I have here problem number 48. Maybe I should put it on the side so you are seeing it. There we go. Maybe I move this aside like that. There we go. Okay. So first thing I need to do is to draw the diagram. I'll put it here. Here's the wall. Here's the beam. And then here's the steel wire. Okay. And here's the angle, theta. I'll come back to this 45. Then I have the length of the wire, the length of the beam. I'm going to call it D for now. Is that okay? I mean, I like to solve this symbolically before I put in any numbers. Here's the angle, and then you have the mass of the beam. So I'm going to call it, so that would be mg, right? So I'm going to call it mg. And then you have a big, not a big mass, but just a mass here. Here it is. And I'm going to call it big M, just to distinguish it. So that's going to be big mg. Okay, and then of course I have the tension in the wire. It's right there, like that. Got it? All right, so I need to know the tension in the wire. One way to do that is if I call this point right here, again, I'm just going to do mechanics here. The best way to do it for me is to use the torque. So what I'm going to do is I want to take the torque about O. So take torque about O. So it's going to be sigma tau about O is equal to, I'm not going to explain the math. I hope you still remember it. So I'm just going to go through it and hopefully you understand what I'm doing. So I'm going to start from here. If this is the center of mass of the beam, so that means the distance from here to here is d over 2. So, and then this is going, the mg here is, what is it, clockwise, so that's going to be negative, right? So that's going to be minus mg d over 2, right? That's the first torque about O due to the mg here, okay? Now the big mg here, and that's going to be minus as well, big mg d, okay? And then now I need to take the torque about about O due to the tension T here. So that's going to be plus, it's a counterclockwise, T sine theta D. There we go. Equals 0. All of that equals 0. These are the only forces that I'm seeing there. Okay? So the D's cancel out. And now I can plug in the values, because remember, I am solving for T. Okay? So now I have here minus the mass, he said, is here it is right here. It is, look at the left side of the screen. It's 4 kilograms. So the small m is 4g. Let me just call it 4g for now, over 2. Is that right? Minus, and the mass is 8 kilograms for the big mass. So that's going to be 8g. And then plus t times sine 45. Remember, this is 45, and sine 45 is square root of 2 over 2 equals 0. There we go. I can easily now find the tension T. So this will give me negative 10g plus what's square root of 2 over 2 is 0.707. T equals 0. So therefore T is equal to 10g over 0.707. So therefore the tension, let me use my calculator for that, 10 times 9.8 divided by 0.707, answer 138.6. So that's equal to 138.6 Newton. There we go. I got the tension. I'm basically done with the problem once I get the tension. Okay. Now, I'm done with this diagram. I mean, the whole diagram is, the whole purpose of it is just to get me the tension. Then, now I know that mu value. Do I know the mu value? I don't. It's not given to me, correct? Oh, yes. No, it's not given to it. What's given to me is the total mass of the string. I thought it's the mu value. Anyway, it's given to me is the total mass of the string. Okay. So I know that the mu value is m over L, right? L being the length of the string, and it's not given to me, but the mass is given to me. So I know the mass. The mass here is 75 gram times 10 to the negative 3 kilogram, that'll be, right? That would be the mass of the string. How do I find the length? Well, again, you just use geometry. So here is the triangle that I'm looking at. This is D, and it's equal to 2 meters. And this, let's call that L, correct? And this is 45. It becomes an easy problem, right? So in this case, L cosine 45 is equal to 2. So L is equal to 2 over cosine 45, which is 2 divided by 0.707. 2 divided by 0.707 equals to 2.83. Okay, so that will be 2.83 meter. Yes, and so therefore the mu value is the mass, which is 0.075 divided by 2.83 meter. So I'm going to have 0.075 divided by 2.83 equals to 0.0265. So the mu value is 0.0265 kilogram per meter. Okay, there we go. So mu, we got that. Okay, we're almost there. Now, what is the fundamental frequency? You saw what is the He said, what is the fundamental frequency? Okay, we know that the fundamental is the relationship between the length and the length and the wavelength is lambda equals 2L. Okay, let me show you a picture of how that looks like. So here is the picture right here. Look at the picture here in the diagram. So that means there is a this string is vibrating at fundamental frequency or fundamental wavelength. What that means, it looks something like that. If I go back to this one here, let me just take this L out. Take all that out. What's happening to it? It's actually vibrating like that. There we go. You see what I'm saying? So it is vibrating up and down like that. You see what I'm saying? And that's lambda is equal to 2L, or L is half a lambda. So now from this I can find lambda. So I already found L right there, right? So therefore lambda is equal to 2 times 2.83. So that will be 2.83 times 2, answer 5.66. So the wavelength here is 5.66 meters. Okay? And then the last thing, he said, what is the frequency? Well, we know that the frequency is V over lambda. And what is V? I'm not done yet. So what is V? Well, V is square root of tension over mu. I already got both of them, right? I got that mu right there, right? And I got the tension from there. It's not an easy problem, I admit, but it's a nice problem. And then from there, I can just plug it in to get the V. So tension here is equal to, what? I forgot it. 138.6 divided by mu, which is 0.0265, and then you will get the velocity, and from there you're going to get the frequency, and I'll just give you the answer. So V over lambda, here's lambda, here's the velocity, and then you work it out, and my answer to it is 13 hertz. Okay, check my solution, but that's what I got. Okay, good. One last problem that I want to work on, and then we'll finish this video. You should be good for this chapter. And the problem is number 49. You know, I'll just give you highlights how it's done. It's not a difficult problem. It can be sneaky maybe though. Okay, 49, let me read it for you from the book. 49 right there. Oh, okay, I didn't need to okay, it says see, this is the picture right here. Okay, so what you have here, you have a string, and or maybe two identical strings, and then between them there is a spring. The spring is stretched, and the spring acts like an oscillator or vibrator, is causing the two strings to oscillate, okay, in some harmonic frequency, standing wave pattern. He said the two strings are of equal length, so they have the same length, and are being driven at equal frequencies. The linear density of the left string, here this one, is 5 grams per meter. What is the linear density of the right string? Got it? Notice something here. This one will give you n equals 2. Look at that. Okay, this one is n equals 3. So definitely the two strings are different. One is thinner than the other, if you will. Okay, so with this information that we're given to us in this problem, what is the linear density of the right string? Okay, it does require some thinking. Okay, you need to sit back and think about it. If we were in class, I would, you know, spend maybe first 5-10 minutes just discussing this and see your ideas about how to solve this problem. But all right, this is not a live discussion here. All right, how do we do it? let's write down what's given to us, okay? Well, let me draw it first. How about that? So let's say we have, here is the left side of it, and then here is the spring, and here they both have the same length. Got that? So here I have 3 nodes. Excuse my lousy drawing. I hope I'm getting better. I still hate that stylus pen. I'd rather be using chalk. I'm kind of old school. There we go. Okay. So here we know that I'm going to call this mu sub L. You know, the length, excuse me, the left linear density, and this is mu sub R. Okay. Another thing is that the lambda sub R, what is that equal to? Well, that will be, remember, go back to the, here, I forgot, what is it? Should I scroll back and show it? Well, I'll just write it down for you. It's basically, I forgot it and I don't want to derive it. Hold on, give me a sec, sorry. There it is. So remember we said that length is n lambda over 2, right? So in this case, lambda is equal to 2L over n. That's the formula, right? So in this case, for our case here, lambda sub r, that's going to be 2L over 3, correct? And then here, lambda sub left is equal to what? 2L over 2, and that's basically L. Yes? There we go. Okay. Continuing on. Also what's given to us, he said the length to the left is equal to the length to the right. So for simplicity, we're just going to call it L. Okay? Fine. And then it also says that the frequency on the left is equal to the frequency on the right. Okay? Now, with this, I can conclude that because we have the same spring here, so the tension on the left is equal to the tension on the right, because we have the same spring. It makes sense that the spring cannot give one tension that's different from the other. So the tension here is also the same. So we have frequency the same, length the same, and my conclusion, the tension must be the same. Got it? Okay. So the main difference here is the following. So now we have, in general, okay, this is just general derivation. If I know that V is equal to lambda F, and V is equal to square root of tension over mu. Okay, this is where I want to, remember, I need to find a link between the two. So this is where the link is going, right here. Okay, so now if I take that and plug it in there, so I'm going to get here lambda F equal to square root of T over mu. And I'm solving for mu. Let me square both sides. So lambda squared F squared equals T over mu. And therefore mu, the general expression for it, is T over lambda squared F squared. There we go. I'm almost done with the problem with those derivations that I have just done, I think. Are you seeing the solution now? So if I know, now I have an expression, a cool expression for the mu value, for the mu, the linear density on both sides. Well, what is mu sub L? Well, mu sub L will be T sub L, lambda sub L squared, frequency sub L squared, correct? And then, excuse me, mu sub R is equal to T sub R over lambda sub R squared times F sub R squared. You see what I'm saying? And I have some ideas about those. Well, how do I find, remember, I'm being asked to find mu sub R, and mu sub L is given to me already. How do I do it? Well, one way to do it, let's get the ratio between the two. That would be the easiest thing in the world. Okay? Look at this. So let's say I want to get find ratio. Remember, mu sub L is given to me, so find ratio. So in this case, I'll just give you a whole page. We're almost done with the video lecture. So it's going to be mu sub R over mu sub L. So that will be equal to T sub R over lambda sub R F sub R squared times, divided, so you flip it, times lambda sub L squared F sub L squared over T sub L, right? All right, let me use a different color. Now the F sub L and F sub R are equal. T sub L and T sub R are equal as well. So I'm basically left with lambda over L over lambda over R quantity squared. I'll come back to this squared later. What is lambda sub L? Go back up to here. Here it is. Lambda sub L is that, and lambda sub R is 2L over 3. See what I'm saying? Plug them in. So I have them there. So I'm going to get here L over 2/3 L. Is that right? Did I do it right? Oh, yes. I have it in my notes there. And then squared, the L's cancel out, so I get 9 over 4. So therefore, mu sub R is equal to 9 over 4 times mu sub L. So that's 9 over 4. What's mu sub L? I forgot. 5 gram per meter, and that will give me mu sub R is equal to 11 gram per meter. There we go. That's kind of a cool problem. I like this problem. You got it, guys? Okay, so I think I'm going to end the video here, and just a reminder again, there is a midterm around the end of this week, okay? Starting on Friday the 24th. I haven't written the midterm, but it should be ready by then, okay? If you have any question, let me know. Goodbye.